For this vodcast, please have note page number 6 in front of you. What we're going to talk about here is the importance of understanding our chemistry reference tables. Here's yet another example of how important it is to understand what you have in front of you and what you'll always have in front of you when you take the Regents exam. Table Q is a homologous series of hydrocarbons. We're going to be referring to this table quite a bit in this vodcast and the vodcasts to follow. Also, on this page number 6, table P, right, and dealing with organic prefixes, terminologies that come at the beginning of a word. All right, let's start with the homologous series in dealing with hydrocarbons. Homologous, for those of you who are unaware of this, means the same. Right, and obviously the hydrocarbons is a combination of hydrogen and carbon atoms that we've been talking about in this particular unit. Now there are 3 different series of hydrocarbons. Right? You can see we've got names, general formulas, and some examples of the name and the structural formula. The first one are called alkanes. Alkanes. A-N-E-S is what we finish with here. Its general formula is CnH2n plus 2. Now the N represents the number of carbon atoms that are present. All right? For example, if we're looking at ethane, you can see that we have 2 carbon atoms and 1, 2, 3, 4, 5, 6 hydrogen atoms. So if we were to take the formula CnH2n plus 2, right? And as we can see within the problem, we have 1, 2 carbon atoms. And remember, the N represents the number of carbon atoms that you have. So if we were to plug a 2 in for the N's, we would get the chemical formula of C2H. 2 times the 2 is 4 plus another 2 is 6. 2 times the 2 is 4 plus another 2 is 6. So the formula for ethane would look like this. Now, number 2, the second example, are the alkenes. All right, and its chemical formula is CnH2n. CnH2n. Right? N still represents the number of carbon atoms that are present. So if we take a look at this example here, structural formula for ethene, you can see that we have 1, 2 carbon atoms present. So if we take the formula and plug in a 2, once again for the N's, what we're going to finish with is going to be C2, 2 times 2 is 4, H4. Now, what makes this different from this is that double bond that is present in between the 2 carbon atoms. So those are your alkenes. Now, the last example is called the alkynes. And the alkynes end with YNES. Its formula is CnH2n minus 2. CnH2n minus 2. Once again, if we plug in the number 2 for the N's, we would get C2H, 4 minus 2 is 2. This is for the alkynes. That formula is going to be different because of the triple bond that is located between the 2 carbon atoms. Okay, so we'll be referring back to this table quite a bit, the homologous series. And just to kind of tie things up here, the homologous series is a group of related compounds. These compounds are certainly related because they involve both carbon and hydrogen, in which each member differs from the one before it by 1 carbon units. All right, and for this particular homologous series, you're going to see a change in carbons from 1 carbon atom all the way up to 10. It does go further than that, but we're going to focus just on the first 10 carbon atoms. Now, note, there are always 4 bonds or 8 electrons around the carbon and the hydrogen. For the hydrogen, there can only be 1 bond around. So if we were to take the structural formula for ethane, you can see that there's a bond here, 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 and here for this carbon atom. And there's also a bond here, 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 and here for this carbon atom. For the hydrogen, there's a bond here being shared with a bond or an electron from this carbon atom, here as well, here as well, here as well, here, and here also. Now for the ethenes, you can see that there's a double bond here between these 2 carbon atoms. So each bond represents 2 electrons. There's 2 electrons there, another 2 there, makes 4, 6, and 8. The same thing is happening on the other side. For the triple bond, for the alkynes, there's 6 electrons right in here, another 2 here to make 8 electrons total for this particular set of units. And you have the same thing happening here, 6 electrons here, and then the additional 2 electrons here to give you 8 electrons total. Now on table P, you're going to notice that there's going to be a listing of the first 10 prefixes. Hopefully you may know some of these from geometry class. If not, you can always revert back to them on table P. Now here's some examples utilizing tables P and Q. All right, what we're going to do is we're going to convert either from the formula to the name or the name to the formula itself. All right, so some key pieces you have to look for here. We've got C3H8. All right, we need to figure out which of the formulas, oops, try that again, which of the formulas, CnH2n plus 2, that's for our alkanes. All right, CnH2n is for the alkenes. And I'll come over here for the last one, CnH2n minus 2 is for the alkynes. Right? We need to figure out which of these formulas is going to work best for number 1. We have C3H8. So if you were to go and to plug in 3 for each of these, which one would produce 8 hydrogens? Right? And it's going to be the first one. Right? If we plug a 3 in here, we got 2 times 3 is 6, plus 2 is 8. It would give us C3H8. Go to our organic prefix. You can see whenever you have 3 carbons, we've got prop. And the simple fact that we're dealing with an alkane formula, you're going to finish with propane, propane gas. All right, the next one, we've got prop again. Right, so we know we're going to be dealing with 3 carbons. This time we're going to write out the formula. But how many hydrogens are we going to have? Here's a dead giveaway, the YNE. That's this suffix right here. So if we plug 3 in for the N, which we already have, we have C3. Plug a 3 in here as well. 2 times 3 is going to give us 6 minus 2 is going to give us 4 hydrogen. So that's the formula we want to write here for problem number 2. Propine. All right, the next one, we have C4H8. All right, we know that if we have 4 carbons, we're dealing with bute. So we're going to start with BUT. All right, now we need to figure out what type of ending we're going to have. We're going to have an ANE, an ENE, or a YNE. So if we take the 4 and plug it in, make it a little messy, but it's going to certainly make our point come true. We put a 4 in here, Put a 4 in there. We got 2 times 4 plus 2 is 10. That's out. Put a 4 in here. 2 times 4 is 8. That's what we're looking at. So our ending is going to be E-N-E, butene. There's another ene. Right, so we know we're going to be using this formula here. Pentene. Pent stands for 5. So we know we have 5 carbons. C5. If 5 is plugged into this formula here, right, we have C5H. 2 times 5 is 10. H10. All right, the next one. We have C6H10. All right, let's go ahead and plug in the 6. I'm running out of colors here. Let's plug a 6 in for this formula, and this formula. Let's see which one spits out 10 hydrogens. All right, so if we plug, I'm going to go to this one here first. So C6H6 gets plugged in here. It's 12. That's too many. Let's go to this one here. C6H, 2 times 6 is 12, minus 2 is 10. That's the one right there. So we've got C6, which is hex. We're going to finish with, because we're using the alkynes, Y-N-E. All right, and then the last one, we have hexane. Hex is 6, C6, and we're using the A-N-E. So we're going to use this formula up here. So we plug in the 6, we get C6H. 2 times 6 is 12 plus 2, 14. H14. Okay? It does seem like it's a lot of work. It certainly gets easier as you continue on. All right, so make sure you have an understanding and you know the importance of table P and certainly of table Q as well, because we're going to be referring back to those two tables quite often in the next couple days.